I'll start with a couple of visual examples, and then move into some examples involving calculations. Here's our first example. In this example, we're looking at the exam scores of 72 students who are in the same class. This is a small population of students. The mean exam score of the class is 80. If we added the 72 exam scores and divided the total by 72, the answer would come out to 80. We're going to pretend that I'm a researcher who wants to know what the mean exam score of the class equals. Since I don't have time to survey all 72 students in the population, I'm going to take a random sample of 3 students, record their exam scores, and then use the mean of my sample to estimate the mean of the entire class. In my situation, the sampling distribution would include the means of all possible samples of 3 students. How would I create that sampling distribution if I wanted to actually create it? Well, to create that sampling distribution, I would need to calculate the means of all possible samples of 3 students that could be selected from this population. That would take me a long time because there's many possible samples of 3 students that could be selected from this population. However, let's take a look at some of the possible samples that are in the sampling distribution. Here's one possible sample of 3 students that could be selected. This sample has a mean of 81.7. We can plot that sample mean down here on this number line. I should have plotted it as an X bar because it's a sample mean, but we'll just pretend that this X is an X bar. Here's another possible sample of 3 students that could be selected. This sample has a mean of 74. We can plot that sample mean down on the number line as well. Hopefully this demonstration is starting to show you the idea of sampling variability. We can already see from this demonstration how different samples have different sample means. One important point about sampling distributions is that the possible samples overlap. The 3 people in these blue circles are a separate sample of 3 people, even though they include some of the people who are also in the brown circles. And we can see that this blue sample has a mean of 75.3. We can plot that sample mean down on the number line also. If I'm planning to randomly select 3 students from this population, any one of these possible samples could end up being my actual sample. Remember that if I randomly select 3 students from this population, the sample that I end up getting depends on chance. Any one of them could be chosen. We're starting to see that most of the possible samples in the sampling distribution have a sample mean within a certain range of the population mean of 80. In other words, most of these possible samples are at least fairly accurate. However, we can see that the different samples have different sample means. And we can see that some of the sample means are further away from the population mean than others. In other words, the sample means aren't all equally accurate. As a researcher, I have to hope that I get one of the sample means that's close to the population mean, and I have to hope that I don't get an extreme sample with a sample mean far below the population mean or far above the population mean. If I get a sample with a sample mean way down here, I'll end up underestimating the mean of the class by quite a bit. And if I end up getting a sample with a sample mean way out here, I'll end up overestimating the mean of the class by quite a bit. But if I get a sample with a sample mean somewhere near the population mean of 80, then I'll end up estimating the population mean pretty accurately. At this point, this graph is only showing part of the sampling distribution, because it isn't showing the mean of every possible sample of 3 people. If we kept going, and we plotted the mean of every possible sample of 3 people, then this graph would show the entire sampling distribution. Let's take a look at some other possible samples of 3 students. The students in the green circles are another possible sample of 3 students that could be chosen, and those 3 students have their own sample mean. Their sample mean is 89.3, which is out there. It's above the population mean. These students in the orange circles are another possible sample of 3 students that could be chosen, and they have their own sample mean, which is 86.7. We're just looking at a few other possible samples. Whenever 2 different possible samples have the same sample mean, their 2 sample means are just stacked above each other. So these 2 samples both had the same sample mean. They both had a sample mean of about 82. So those 2 sample means are stacked above each other. And now we have 3 samples that all have the same sample mean. So these 3 sample means are all stacked above each other. Once the sample means begin to stack above each other, that's when the sample means begin to form a shape that we can see in this graph. And if we kept going, these sample means would keep building up to form a shape. And then once we actually calculated the mean of every possible sample of 3 students, we would have the complete sampling distribution for the sample size of 3. And that sampling distribution would have a certain shape. Notice how most of the possible samples have a sample mean within a certain range of the population mean. The population mean is the center point of the sampling distribution right here, and as you go further away from the population mean, you start to see fewer and fewer sample means. Let's now look at an example with a different sample size. If I wanted to randomly select a sample of 10 students from this population and calculate the mean of those 10 students, then my sample would be a member of a different sampling distribution. My sample would be a member of the sampling distribution of all possible samples of 10 students. Let's take a moment to look at some of the possible samples of 10 students that could be selected from this population. Here's one possible sample of 10 students, and these 10 students have a sample mean. Their sample mean is 80.2. If we add their 10 exam scores and divide the total by 10, we get a sample mean of 80.2. We can put that sample mean down here on this number line. I should have probably, well, actually I think this is pretty close to 80.2, so I think I did put it in about the right spot. Here's another possible sample of 10 students in the green circles, and these 10 students will have their own sample mean. If we add their 10 exam scores and divide the total by 10, we get a sample mean of 81. So right here, we have the mean of the 10 students in the orange circles, and right here we have the mean of the 10 students in the green circles. Those 2 samples are 2 different possible samples of 10 students that could be chosen from this population. Now let's look at a different possible sample of 10 students that could be chosen. The students in the blue circles are another possible sample of 10 that could be chosen, and they have their own sample mean. If you add their 10 exam scores and divide the total by 10, their sample mean comes out to 82.2, which is about right there. And you might have noticed already that the possible samples of 10 students have sample means that are clustered closer to the population mean. And you might have noticed already that the possible samples of 10 students have sample means that are clustered in closer to the population mean. And you might have noticed that the possible samples of 3 students that we looked at earlier had sample means that were spread out further away from the population mean. That's why larger samples are considered to be more dependable and more accurate. If you calculate a sample mean with a large sample, your sample mean is likely to be closer to the population mean, because when you select a large sample from a population, most of the possible samples that you're drawing from have sample means that are pretty close to the population mean. A smaller sample is more likely to give you an extreme sample that highly underestimates or highly overestimates the population mean. You might have noticed already that the possible samples of 10 students have sample means that are packed in closer to the population mean, and you might have noticed that the possible samples of 3 students had sample means that were spread out further away from the population mean. That's why larger samples are considered to be more dependable and more accurate. When you select a large sample from a population and you calculate the mean of your sample, you're likely to get a sample mean that's close to the population mean, because when you take a large sample, most of the possible samples that you're drawing from have a sample mean that's pretty close to the population mean. You might have noticed already that the possible samples of 10 students have sample means that are packed in closer to the population mean. And you might have noticed that the possible samples of 3 students that we looked at earlier had sample means that were spread out further away from the population mean. That's why larger samples are considered more accurate and more dependable than small samples. When you select a large sample from a population and you calculate the mean of your sample, you're likely to get a sample mean that's close to the population mean, because when you select a large sample, most of the possible samples that you're drawing from have sample means that are close to the population mean. So if we moved on and we kept looking at more possible samples of 10 students, we would still see that most of the possible samples have sample means close to the population mean. And if we actually took the time to calculate the mean of every possible sample of 10 students, and we plotted those sample means in this graph, we would see the complete sampling distribution for the sample size of 10. Before we move on from this example, I wanted to mention that there's actually a different sampling distribution for every possible sample size. So far, we've only looked at the sampling distribution for the sample size of 3 and the sampling distribution for the sample size of 10. However, since there's 72 people in this population, each possible sample size between 1 and 72 has its own sampling distribution. If we wanted to, we could look at all 72 sampling distributions. We could look at the means of all possible samples of 2 people, the means of all possible samples of 3 people, the means of all possible samples of 4 people, and so on. At this point, we'll move on to some other examples, but first I wanted to explain one of the most important concepts in the topic of sampling distributions. This concept is called the central limit theorem. The central limit theorem allows us to predict the shape of the sampling distribution of sample means without having to actually create the sampling distribution. In other words, it lets us predict what the shape of a sampling distribution will look like without actually having to calculate the mean of every possible sample. According to the central limit theorem, the shape of a sampling distribution is predictable based on the shape of the population and the sample size. At this point, we'll move on to some other examples, but first I wanted to explain one of the most important concepts